Better. Okay, so there's a reason I brought props today. So remind me, Euler's formula?
Vertices plus
Minus that just plus
nice. Next.
equals 2.
Plus F minus E.
Just say like vertices minus faces.
N minus M, what was that?
M plus F minus E equals to 2.
Oh, and always.
Okay, so, and what's important is, the most important thing I can remind you is, this is only true for planar graphs. Okay, so when you get to the final exam, that doesn't apply to every graph, right? It only applies to planar graphs. That's kind of important. Because most of the graphs you have looked at this point probably aren't necessarily planar. Okay, so one more time, Euler's formula. Euler's formula is what? N?
Minus E plus that.
Okay, so I don't know. Sometimes I like to write it as E. The book writes it as M, where M is the number of edges. N is the number of vertices, F is the number of faces. And you know, so the key that in a planar graph, and remember there's the outside face. There's the outside face. Every edge is in exactly 2 faces. Okay, this sort of is what drives exactly 2 faces. So this sort of helps us to establish the results here on the bottom of page. On the bottom of page, well, it helps us to actually establish Euler's formula. But if we look at a graph, if we look at a planar graph, and let me just take this. We haven't spoken much about multiple edges, but this is a planar multigraph. So unless you make it distinct that it's a graph, it's planar, right? Right? None of the edges cross. It's a multigraph because I have in between these 2 vertices 6 edges, and I know that. Notice that I have 7 faces. 1, 2, 3, 4, 5, 6 faces. Okay, so it's important as we establish this that we establish the results. By the way, does this satisfy what? How many vertices? Let's see. N is 2. Number of edges? 6. N minus, so 2 minus 6. Is that right? 6 edges? 6 edges, and how many faces? So 2 minus 6 plus 6 equals 2. So it works for multigraphs as well. Okay, but multigraphs have the problem that you know, we don't know. A face could have as few as 2 edges. In fact, we haven't talked much about this. A face, we could have 1 edge. We could have a face that's 1 edge. Okay, so it's something that we haven't spoken about much. Graphs that have multiple edges and graphs that contain loops. But as long as you're not crossing edges, as long as 2 edges don't cross, as long as you can draw it so they don't cross, then in fact you have a planar graph, it satisfies Euler's formula. Okay. That's maybe the last time I'm going to draw multiple edges. Okay, so again, starting with Euler's formula, there's a relationship between the number of edges, and the number of vertices, and using the fact that if we have a graph that's not a multi-edge, that's not a multi-graph, then I have a relationship between, and one more time, every edge is contained in two faces. Let me go back to this loop thing here. Okay, even this edge is in two faces. It's in this face, and it's in this face. Okay, and it doesn't matter where the loop is. So maybe I have a loop over here. So even though I have a loop here, it's in this loop, this edge here is contained in this face and this face. So this idea that every edge is in exactly two faces is important for proving Euler's formula. Okay, so if I don't have any multiple edges, if I don't have any loops, then in fact we know that the relationship between the number of edges, m, and the number of vertices, so I know that m is less than or equal to 3n minus 6, which this told me that K5 is not planar, because K5, let's see, has n equal to 5, m equal to 10, thank you. So if Euler's, this must be true, m is less than or equal to 3n minus 6, then in fact m is 10 would have to be less than or equal to 15 minus 6. 10 would have to be less than or equal to 9, which we kind of still know that that's not true. Okay, so that showed that K5 was not planar. For K33, we knew that all of the faces had to have at least 4 edges. And in fact, we know that in K33, and in fact in any bipartite graph, in any planar bipartite graph, in any planar bipartite graph, every face must have, what can you tell me about every face? Must have how many edges, at least?
3.
4.
Oh, 4.
Why 4?
Because it's bipartite.
Because it's bipartite. So if I had a face that had 3, what's wrong with that? It's an odd cycle. Bipartite graphs don't have odd cycles, so we know that every face must have 4, and therefore we get so which contains no C3. In fact, 8.7.7 says that if G contains no C3s, then the number of edges must be less than or equal to 2n minus 4. So no C3s, m is less than or equal to 2n minus 4. And if I look at K33 I know has no C3s. Why do I know that? K33.
It's a bipartite.
Because it's bipartite. K33 is bipartite, and therefore the only cycles K33 have are even. I mean, you can even say more. It only has 4 and 6 cycles. Okay, there's no 3 cycles in here, so I know that this inequality gives me a bound on the number of edges. So m is less than or equal to 2n minus 4. How many vertices here? There are 6 vertices. So 2 times 6 minus 4 would have to be greater than or equal to how many edges? In K33?
9.
9 edges. So if this was planar, if K33 was planar, 9 would have to be less than or equal to 12 minus 4, which is 8. And I hope you know that 9 is not less than or equal to 8. Okay, so using Euler's formula, we now know, even though you spent lots of time trying to prove or trying to draw K5 and K33 in the plane so that no edges cross, we know they're not planar. You can't do it. Okay, is that clear?
And just to double check, we're saying planar implies these inequalities, right? And planar no C3 implies that inequality.
Right, but
that's not reversible,
and
is it?
I'm applying it by saying, well, if this was planar, then
Right.
we would have a contradiction.
And to double check, those are not reversible, right? We can't say if a graph is m less than or equal to 2n minus 4, therefore it's planar,
No,
can we?
no.
Okay.
Right, and you can, you know, n and m can be big, right?
Mhm.
So start with a K5. Okay, the K5. And now just put a sparse graph. Oh, let's not even, we don't even have to, just, that doesn't have too many edges. So it meets the inequality of the number of vertices versus number of edges, but it certainly is not planar.
Cool.
Okay? Yeah, so it's not an if and only. Only works if you know that it's planar.
Sure.
Okay, so I asked you to look at questions number, so a subdivision. So if I take a planar graph, so if I take any planar graph, I'm just drawing this graph. It's nothing special. That's too many. Let's put this in. Okay, there's the planar graph. I know it's planar because I drew it without any edges crossing. I know that there is no odds. There's no subdivided K33, no subdivided K5. And if I take a planar graph and I subdivide the edges, so if I make, instead of this edge, let's make it a path. Instead of this edge, let's make it a path. And just, do that for all or some of the edges, then the graph remains planar. The graph remains planar. So, for example, at the top of page 345, the authors start with a W7. I'm guessing that's the wheel on 7 vertices. And right next to it, B is a subdivided W7. All we're doing is putting vertices, instead I'm replacing an edge with a path. So I can replace an edge with a path. Okay, so we can subdivide this. And if Euler's, we still have K33 and K5 sort of determining whether the graph is planar. So I'm going to jump down before I ask you the answer to these. So if you look at theorem 8.7.12, these two graphs, K5 and K33, sort of determine, they completely determine when a graph is planar up to vertices at degree 2. So if G contains, let's define a subdivision of G is adding vertices of degree 2, to edges. That's not a very technical term, but if I take let's at this point imagine that it's planar, and I can throw in vertices of degree 2 by subdividing any of the edges. As many times as I'd like. If the graph is planar, then when I subdivide these edges, the graph is still planar. If the graph is not planar, and I subdivide edges, the graph is still not planar. Okay, so adding these vertices of degree 2 doesn't change anything. So now looking at problem figure 8.7.7. Okay, verify that these two graphs, that the A is a subdivided K5, and B is a subdivided K33. So what I want to do is I want to find sort of the underlying K5 or K33 and show that instead of an edge in some places, I have a path. They could have labeled the vertices first to make it a little bit easier to talk about these graphs, but.
So if I get rid of all the ones that have degree 2 and just make this be an edges to the path, same thing to here.
All right, just to keep
I mean, thank you.
In this context, pretty common ideas to label the branch vertices.
The branch vertices meaning the ones not subdivided.
Right, those which are represented in the original graph. Is that what you did?
What I'm trying to do.
Oh, I see.
Okay, so here's graph A. Here's graph A, and I want to replace paths, induced paths, not just any path. I want to be able to replace paths with an edge. So an induced path meaning that I only have vertices of degree 2 on it, with an edge so that I come up with a K5. And hopefully it's pretty simple if I replace this path with that edge, and I replace this path with this edge, then I have a K5. A K5. Okay. For part B, again, I've replaced some of the edges in a K33 with a path. So I can look at the 3 vertices sort of in the middle, that forms one of the parts. The two vertices on the bottom and the one vertex all the way on the top forms the other part. And then edges between the two parts, some of those edges are subdivided. So in fact, I have 3 subdivided edges. Okay, I hope I don't have to draw that. Now, what map makers and mathematicians worked on from the middle 1700s through the early 1900s is proving that these two graphs, K33, K5 and K33, in some way characterized planar graphs. And at the bottom of page 345, there's the theorem, Kuratowski's theorem, 1930, and the history goes at least 200 years before that G is planar if and only if it contains no subdivided K5 or subdivided K33. They're just dying to get in here. So that's Kuratowski's theorem. Now, in the 30s, people thought that was the key to the four-color theorem. Remember, take any planar graph. Take any planar graph. Doesn't have one of these. So you take your favorite planar graph. Here's one of my favorite planar graphs. No edges cross. The only place that edges meet are at vertices. Then, in fact, I can color the countries of this graph with at most 4 colors. Sometimes I don't even need 4 colors. Okay, sometimes I may only need 3 colors. But if I take any planar graph, the conjecture was, and this is for hundreds of years, this conjecture lasted, there was that, in fact, we could color the countries or the states or whatever you want to call these, the land masses, whatever you want to call them, we can color them properly. What do we mean by proper coloring? What does that mean? I wanted to color the United States, so what was the case?
No adjacent states of the same color.
No 2 states that share a border,
Sure, border.
which share a part of a border, more than a vertex. Like 4 corners, we could have colored 2 states. Everybody knows what I'm talking about, 4 corners? Where's 4 corners? Arizona, New Mexico, Utah, and Colorado. I think there's another 4 corners somewhere over here. Tennessee, Virginia, I don't know. Don't look. It'll be embarrassing. Okay, so notice these 4 states don't share any border. Okay, don't share, these 2 states don't share a border in these 2 states. So I could color this color 1, and this color 1, and this color 2, and this color 2. And in fact, every planar graph can be colored with at most 4 colors. Some can be colored with 3 colors. Okay? So that was Kuratowski's move towards helping to prove the 4-color theorem, which it still took quite a bit of time. Okay, so before we get to the fun problems, so I asked you to take a look at problem number 1. So this is on page 346. Determine which of the graphs are planar. They all look like they have problems. They all have edges that cross each other. Oh, and look, our favorite, the Peterson graph is there. We haven't drawn the Peterson graph in a while.
Which one?
It's worth drawing it up.
差就是
第一个可能不是，
可是他画的都看起来都交叉的。这个不是。
不是，它交叉你也可以调整一下，对吧？调整到把线调整到这个地方。
还有别的办法吗？
有啊，刚才不是有？
就摁进来小没有那个。
不是，是那个刚用的把气声，刚学的那个。
就不 T 不 K5 然后 K3。
对对对，不是 contain， 是 subdivision of the K5 K33 K5 但是如果看得出来就不需要看到了。
数学题怎么能写有什么区别？
Maybe D is a good place to start. I mean, how hard can that be?
我还在看 B， 我想试试那个怎么看K33？应该不是。我觉得你看这两条线，其实我快扒拉了，它也必须要形成在一起。
So if a vertex has a degree of 3, it cannot be one of those things that we're subdividing? Is that what you're saying?
Well, what?
我
So,
也收到了一封邮件。Jones。
okay, so the other one, okay, so for example, we made this thing a path.
Correct.
Okay, and all the things along the path have only degree 2.
Correct.
So if this thing had something like that, could we have still done that thing?
Well, no,
Okay,
no.
okay.
You can only replace, we're replacing paths, induced paths
Yeah.
with edges.
Okay.
我觉得这个线一多就真的很恶心。
Oh, induced paths. Okay, so meaning using all the edges along the path.
Correct.
Okay, very good. Thanks. What do you think about that second one?
I think it's planar.
Yes with a question mark? Okay.
It's
I
not.
agree. It's not.
Okay, because I'm trying to find this up graph.
Oh,
So it's a K3. 哎呀，我分给你听一下。Pick a vertex that has 3 degree 3.
maybe we should have each table work on a different.
And that means
我有看了晕车的感觉。
also go to the same 3 times.
Are you holding it like this? So you're saying
This is letter B. Do you understand?
第二个部分
this thing?
Yeah.
你画那么大有什么用啊？
I'm sorry. I was
没有用。
But this,
I was just in
第
myself.
二个应该不
Was that
是
different
第
graph?
C 我判断不太出来，
I feel like these
第
are
二个
this.
为什么不是
It looks like
因为
That's
？It's which
可以
one?
感受
Oh
到
yeah, yeah.
是两
Right.
条线，
树的。
Oh yeah, that one's
这两条
complicated.
线如果把它们
Different B.
都扒光
Okay,
的
gotcha.
玄学。Okay, so you're working on
无
this
论
one.
如何里
Yes.
面都会交叉，因为里面都已经是个 planar graph，然后如果把这两条线无论如何都会交叉在一起，
这样能作为判断依据。
我觉得是可以的。
有什么讲出来的？
没有交叉，
哎呀，然后
Question? Answers?
no answers。
No answers. No, you gotta have an answer. What do you believe?
for a K5.
What do you think?
Minor or
So,
subdivision
well,
to exist. there
I was
needs to be
trying to
one
use
versus degree.
the theorem 8, 7, 12 to identify the planar graph. but,
Okay.
4 vertices.
Right.
So which one in particular are you looking at?
Check it out. I think we can do
I'm looking at the
identity
C.
to show that
C.
it's not planar.
Okay.
Oh, there are 5.
All right, let's look at C for a moment.
The top left, top right.
Wow, that looks like a hard graph to, let's see if I can draw that
But
graph.
look, we got
Easy.
3n minus 6 is 21.
就是因果对称，我觉得对
Okay,
称
C.
就
Is
很难。
less than
I gotta bring the book over here.
minus 6.
If you take out the degree two,
第一也应该会较长。
you're left with this. And so in this one, you can pull on the one side, but that means these two crossing. This guy's the problem. So if you take out this degree two, and this degree two, you're left with this.
第一可能是
Yeah, is that
K
it?
3 3
And so you can pull this edge out here.
再把那
So
两个
that's
去掉
what
过
it
来，
is. But you can't pull this one out because we're
可能顺
crossing
着 K
lines on
C
the
3
outside.
再去掉那样。
And you can't pull this one out because it's.
Okay, that looks, is that C? Kind of looks like C.
So these two.
Yes. But it's not
In
quite,
B?
because we have,
This is what.
Okay, so let me ask a question. Is this graph bipartite?
but that degree.
Yeah, these
Can you tell whether this
Right.
graph is bipartite?
Vertices. Yes. Because
You can tell that it is or it isn't?
that group up there are the ones with.
How big is this cycle here?
Vertices. But these two.
Oh, it's the old cycle.
One of
So,
the-
so this is not bipartite.
Degrees.
Okay,
This
so,
one, which isn't
so,
accurate. So it can't form a K5.
I'd like to show somehow that there is, I mean, so I could try and find an induced,
So the idea is, does it?
sorry,
So what
a
we
subdivided K33
is like a box thing.
could try and find a
And this thing.
subdivided K33.
And that's not the original graph, don't tell me.
Okay, can, is,
Right, so
I mean, the question will be, is that on cycle gonna bother us? Okay, so let's, if we wanted to find a subdivided K33 here, well, I only have, there's 9 points.
So this, without this edge,
I think so. Wait, is it any subgraph or can you do subgraph?
So that there
And,
is,
and, so what'd you try? What'd you,
so we've got a subgraph. There's a
you could do
subdivision
this
of
at
K3.
which is a
Okay, I was thinking of that.
okay, does it help? How many edges does it, how many vertices does it have?
But it is.
N is what?
Because you have to,
Yeah.
you have to get rid
You have to get rid
of those two and that one.
How many vertices?
9
That makes
vertices.
sense.
9 vertices.
Yep. So
How many edges?
these three is one of them hard to have.
Do I use E or M? How many edges?
Yeah. There's actually also a K5.
No, there is not. You are lying.
It's a subdivision. It's a subdivision that's a subgraph. Right, so we can lose this edge. And
How many edges?
13.
7?
13.
13. 13 edges? Well, let's see, we haven't used some of these, some of our known facts. This is a graph. What's the degree of this vertex? Let me write the degrees down.
Okay, remove this.
3,
Like this.
the degree of this one is 3, degree of this one is 3, degree of this one is 3, 3, 3, degree of this one is 3, degree of this one looks like 3, and the degree of this one is 2. Okay, why does it help me to write down the degrees? Some of the degrees is, okay, so 3, 1, 2, 3, 4, 5, 6, 7, 8, that's good. I have an even number of odd degrees, so I have 8 threes. 8 threes is 24,
So if we draw.
plus 2 is 26. So how many edges?
So that means we're totally covering all the bases.
Number of edges is 13.
Okay. This is what it looks like.
So
This is
the
the
whole
one
vertex.
vertex.
These two go up like that.
See, I don't know anything about faces, so I can't necessarily use Euler's formula yet.
And these are the subdivision you go with. Doesn't matter. You can look at this subgraph without this edge.
Without this one.
And then this,
But this one, but we're moving.
So if I can't use anything about the number of edges and the number of vertices. The only thing that's left is what?
This, we can't remove this one because it's
is this.
The
Is-
theorem says.
So I can use
By
this?
getting rid of any vertices.
I can try.
Okay.
Okay, so, but this,
Okay.
so,
Okay.
the problem is that, this would say that every face has, yep, it's a multigraph, every face has at least 3 edges. So the number of the number of edges has got to be less than or equal to
Like that.
3 times,
Okay.
3 times n is 20, 3 times 9 is 27, minus 6, 27 minus 6 is 21, is got to be greater than or equal to the number of edges.
It's pretty easy to
That's
see.
pretty-
Just
pretty
drag
much
this one
true.
up, And it's the normal pentagram shape.
Okay, but
So that doesn't help us much.
But-
And we don't know that it's
to go from
bipartite, so I
here
can't use any of the other results. I don't know anything about faces.
You can't get
So the
rid
only
of
thing
vertices.
left is, can I find a subdivided
No.
K33 or a subdivided K5?
Oh, never mind, I'm sorry, you're saying this is the pattern.
Just, well, more than 5 vertices, so
There's certainly more than 5 vertices, absolutely. Let me build on that. If I had a subdivided K5, if I had a subdivided, where am I pointing? A subdivided K5, then what would be the degree of every vertex? It would have to be 4. Or more. But,
oh,
so I can't have a subdivided K5 here. There's no subdivided K5.
So I'm saying C has a K3.
Yes? Because if I had a subdivided K5, one more time, if I had a subdivided K5, then I'm just going to write this, so there would have to be a path, they would have to be disjoint paths from every vertex to the other 4 vertices.
So I can get to here.
Disjoint would mean that the min degree would have to be at least 4.
Can get to here. Can get
So there's no subdivided K5 there.
to here. Can get to here. So it's K3.
Okay, so the only thing that's left is a subdivided K33.
What do you mean coming from?
So is there a subdivided
Like
K33?
that, right, so you can draw K5 or a K4 like this, or you can draw a K4 like this. So that's a common way.
So how might you start this? So let me help you out. What if I choose these 3 vertices? And I choose these 3 vertices. I know this vertex here isn't going to help us much, because it's only got degree 2. So are there disjoint paths or edges between every square 3 to every circle 3? So I need disjoint paths. I need a disjoint path from this 3, notice that's a path, to that 3. Notice these, of course, they're not very interesting paths, but they're paths themselves. Okay, so we've taken care of the top vertex. What about the bottom vertex? No, sorry, what about this vertex? So there's a path from this square 3 to this round 3, round 3, round 3. And the only one that's left is from this square 3 to the other 3 round ones. And so we have a subdivided, and we can actually draw this out. So there is my subdivided K33. Let's just make sure you see that. Here's my 3 square points. And here are the 3 circle points. And this square point has edges to 2 of the circles, and then a path over here. Let's see, this square has an edge to here and here, and a path over to here. So this vertex it's to 2 different ones. In fact, I just can't do it because I know it's not planar. I know this graph is not planar, so I can't draw it without crossing edges. So here's an edge, is cross. I can't do it. But here is, again, a subdivided K33, so this one goes to, let's see, this one goes to here and here, this one goes to here, so this one has to go to here and then there's a path from here. Everybody, can you see that? I haven't used any of the edges twice, and I have disjoint paths from the 3 square vertices to the 3 round vertices. Some of the paths are edges. So that is a subdivided K33. And notice, it actually isn't subdivided that often. Only 3 of the 9 edges are subdivided. Okay? So since it contains a subdivided K33, is this graph planar? No. Okay, is that clear? Okay, and that's the challenge, is trying to figure out where the K33 or the K5 is. Okay, and a good indicator is if you're having trouble drawing these things. So how hard? I'm going to look. Number D. D. Letter D has, it's an 8 cycle. I think that's an 8 cycle with 3 more edges. Okay, the question still is that planar? Okay, now let me again rule out that you can't have a subdivided K5. Someone give me a reason why you can't have a subdivided, and then this is number D on page something.
346.
346, number D. Why can't I have a subdivided K5?
Degree 4 vertices.
You have to have degree 4 vertices. Whether it's edges or it's paths, you got to have degree 4 vertices. And this is it regular degree 3? Not even regular. Its max degree is 3. So there's definitely no K5. It's definitely no subdivided K5. So either you're going to draw it in the plane. When I say draw it in the plane, that means draw it without any edges crossing. Or I'm going to show you the subdivided K33. Which one is it?
Subdivided case.
You can't draw it in the plane, so there must be a subdivided K33. Okay, who's going to tell me where that is? So here's the graph. It's only got 8 vertices in it. And 3 more edges. Who's going to tell me, if I label them, will you tell me what the two parts are? 1, 2, 3, 4, 5, 6, 7, 8.
1, 6, and 3.
1, 6, and 3? 1,
Yes.
6, and 3? 1, 6, and 3?
2, 8, 5.
2, 8, and 5. 2, oh, sorry, let's make those squares. 2, 8, and 5. Now many of the edges are there. Like 1, he's adjacent to 2, 8, and 5. Okay? Let's see, 6. 6 is adjacent to 6. Here's 6. He's adjacent to 5 and 2. And I'll come back to 6 in a second. And where's the other round one? Let's see. And 3. 3 is adjacent to 8 and 2. So all I need is a path, disjoint path from 6 to 8. A disjoint path from 6 to 8. and a disjoint path from 3 to 5. So that goes there, between 8 and 6. And this point is 4, and this point is, what do we say, this point is between 8 and 6 is 7. Okay, and there's my subdivided K33. Questions? The Peterson graph? F? Now, let me, before you start pulling your hair out. Now, you know, the Peterson graph, just shrink that outside cycle, it looks like a K5. So just sort of collapse it in, and it's a K5, but you can't do that. Okay, if I'm gonna have a subdivided K5, what can you tell me about the degree of the points in that subdivided K5? They must be at least 4. This graph, the Peterson graph, is regular of degree 3. I haven't drawn the Peterson graph in a while. I drew it on the first day. So there's no way that we can find the subdivided K5. Can you find the subdivided K3? Sorry, K33. Got very quiet. I'm gonna be right back. I brought the wrong thing with me. I'll be right back.
我在看的时候，我在想是还是不那个什么，K33的这种，但是我觉得就是你看这里有一个 out cycle，我觉得可能要把它变成 sub 才能是不是 out cycle，而是
Using Dalton's strategy from the previous one.
Which was what? Did you do the K33?
Yeah, so, and so what I was misunderstanding was that, because I had asked him, I had asked Dr. Jacobson, like, okay, so,
一个 bipartite graph 有可能还有 out。
so these are all degree 2s, so those are why we can't, or that's why, but, you know, I had asked him about like this, and then he said, well, we can't do that. But Dalton pointed out, all we need is a subgraph, so we can look at that subgraph.
但是
Right,
it's
it's-
这个 subgraph
This question was about, is it exactly a subgraph?
continuous subgraph。
I see, okay, I see. But yeah, contains a subgraph isomorphic to a subgraph. So here we can definitely get rid of things, and then they're degree 2s.
Right.
Don't use those things later on,
Right.
or
This
before
graph,
for
yeah,
that.
it doesn't have any vertices of degree 2. You'd be pulling your hair out for a while.
And so what did you do on the Peterson one?
Oh, so,
Yeah. And
And
then
then just get
none
rid
of
of
the
the other
path
four.
is crossed.
Yep. One important thing when you're looking at these paths is that they do not intersect at all.
Yeah.
mhm.
Super important. And they don't.
I mean, this one, you know, we've got this path and that path, so by that point, we can just draw that one out.
Right, yeah, no, by intersect, I mean, they can't share vertices.
Oh,
Along the way,
Right.
along the path.
So you couldn't, you know, have
Yeah.
this path to here through this vertex and this path to here through that vertex. That would
right,
definitely,
right, I see what you're saying.
got an old homework I did.
只要是能是3D，
Okay, how you make it out?
3D 的就可以导不会冲。
G has a K5, just get rid of everything in the middle.
G, what would you say, G?
Yeah,
G has a K5?
I think so.
Yeah, just in the subgraph without that center vertex.
Okay, we have a claim that G has a K5, a subdivided K5.
Division.
Yeah.
Okay, so I'm gonna guess you're gonna use the outside 5 cycle.
That is correct.
Okay, so we use the outside 5 cycle, and now I have to go from any one point to its 2 opposite vertices
Mhm.
with a path. Okay, so to go from the top to the 2 bottom vertices, well, there's only 2 paths I can take. So I'll take those 2 paths. And in fact, to go from any 2 vertices, I'll just take the path of 2 edges that goes through those middle points. And every edge, no edge is used more than once, every vertex is used once. Okay? So G has a subdivided K5. Now, I'm not saying that's fine, that shows that it's not planar, doesn't have a subdivided K33.
突然的自白。
二十面骰子，以前玩龙与地下城的时候用过。你们玩过龙与地下城吗？
我看直播在网上，
可以，对，就是那个，
这是几面？
那个是要自己编情况是吗？
有剧情，然后
这个是
十面骰，
还有
可以 put on my hat of disparity.
谁知道最大的报说这是这个10面是20。
是。
On my hat of disparity give me advantage. So
Okay, those are not to be rolled, those are not rolling dice, those are.
You put dice on the table and can't.
Okay, so just
So
to
any
sort of
7 is 10.
wrap life up, so this idea of drawing things in the plane without edges crossing has a very long and rich history. You know, before the word graph was ever introduced, before people even thought about vertices and edges, the Greeks actually were doing this has a flavor of geometry to it. There is a flavor of geometry to this. And so I put a 12-faced and a 20-faced regular solids on each of the tables. And if we look at each vertex, each of the vertices, I don't know what they're called, points, where the edges meet. Is that called a vertex? Okay. So we've got one has 12 vertices and one has 20 vertices. And the Greeks were pretty interested in deciding whether you could draw the red one, that is red, okay, whether you could draw the red one in a plane without any edges crossing. Okay, so I want you to take a few minutes, and the same thing goes for the blue one? Blue? Yes. Okay, so the same thing goes, so we have 12 vertices. Notice that the red one is regular of degree 5, and the blue one is regular of degree 3. When I say regular, at every corner,
Yeah.
I'm gonna have a vertex. And notice every vertex sends 3 edges out. For the red one, every vertex sends 5 edges out. And the question is, can you draw these in the plane without edges crossing?
我觉得
Okay, so take a few minutes.
plane
Again, this is just a sort of wraparound, although graphs and the idea of graph theory really didn't come into its own until the middle 16th century. The Greeks were thinking about graph theory without calling it graphs. Okay, so they were looking at these problems.
真翻译成讨论是吧
Oh, yeah, it helps if I have this on. Good, okay. Okay, so again, can you draw those? Can you draw those, the corresponding graph? Does everybody understand? The red one has 20 vertices,
下面再放大
20 vertices, and is regular of degree 5. And the blue one has 12 vertices and is regular of degree 3.
放大
And the question is, can you draw those in the plane without edges crossing?
这是在下面的分都行
Did you say it goes back to the 16th century?
就
Well, the first, yeah,
Like
as
1500s?
soon as they were making maps.
Oh, okay.
As soon as cartographers were making maps, this question of drawing these things planar, the word graph didn't come to be until the middle 1800s. I mean, edges and vertices, yeah, that came much
So
later.
even Euler wasn't even calling it graphs?
Oh, God, no,
He was-
no, yeah.
Oh, okay. Gotcha.
4分不是已经结束了大致
I think vertices and edges
我也想买一支口红
came from
我想买一支口红
geometry.
From well, a lot of it came.
Euler was studying solids.
Solids,
When he
right.
came up with Euler's formula.
Right.
V plus C or V minus C plus F.
But he didn't use V, he didn't use V and
这
E.
要花20年
I was pretty sure of
这
that.
山那
哎
有
等等我们
It's
只要
not
时
like
间
a
然后拼着
this is where
用那个 Eulers formula
that formula written down.
嗯
Maybe
Could be.
check.
嗯
Because, you know, back then, of course, a lot of what we talk about now didn't exist. He invented a lot of
我知道 n 有多少个一共有20面每个面有几个字哎等等这个简单
Yeah, not gonna find
有
it.
一个
Although the
He looked at Euler's
history of Euler's formula might bring you back to Euler.
2除以
I think we can calculate the versus number and the edges number.
不可能啊
怎么会这样？
怎么会这样
怎么会这样？
Euler's formula graph is also
它有几个边？
不知道每个面有5个边
现在多少个点
每个边对每个边可以重复2次所以是
没有，一个 vertex 里面不能重复。
一个 vertex 但是一个 vertex 应该是重复了3次
这里都是多少个数
这是5乘12除3这个5乘12除3
I see, so you just started with like
30个边，30个边。
12 faces.
对对对对
That's
是的哎你看看你
你们怎么 I see.
就一个边重复2次
Okay, so n is equal to 哦，そうか。
所以然后你来比呗这那叫什么 m 小于30小等于3乘20减6
这是20个点吗？
嗯
1、2、3、4。
not bad.
You got it?
I think so.
什么是30
Well, actually,
感觉中的好神秘我不能看
I think I might have just drawn a 12 or regular 3 graph that
完
didn't
全小于等
not have anything to do with that shape.
根本没法用这个看一看
对，那他就没有用我这边吗
对没有
？OK，好，行。这个呢？
K33呢 K55呢
这个怎么数呢？从这个数，20乘，这有几个点？20乘2，这有几个点？是吗？
12个点。
嗯，
1、2、3、4、5、6、12个点，12个点，12个点都要变。
Oh, I see, and then the infinite face is like is the opposite of the one in the middle.
Oh, that's really good.
Thanks. Got the idea from
Yeah, that was really good. I was thinking, how could you flatten it out?
okay, so, you got it? Both of them? So this one, what is it? The X and the, so you think you can draw this
Shouldn't
one?
a better face be a pentagon?
So we have 20 vertices,
yeah, you're.
and how many
So
edges?
these are 4 faces.
So
Do we have 30 edges? We have 20 vertices of
I also
degree
started running out
5.
of room, so I just kind of.
20 vertices degree 5 is 5 times 20 is 100, divided by 2 is 50 edges.
我感到有些惊慌。
You mean this one?
Oh, sorry, so how many vertices are there? Are there 20 vertices there? Okay, so I see, so we have degree 3, okay, so we have 20 vertices, degree 3, and 12 faces. Ah, yes, okay, so the blue one, the 12-faced one,
So I worked on the first one.
the 12-faced one. Let's talk about the 12-faced one. So how many vertices are there on the, I think it's blue, on the blue graph, on the blue dot? How many vertices? 20. Each vertex has degree what? On the blue one?
3.
Degree 3. So I have 20 vertices at degree 3. So how many edges?
30.
30. So I have how many vertices?
Vertices 20.
20 minus 30 plus how many faces?
12.
20 minus 30 plus 12. Well, yeah. So in fact, the formula works. The formula works, but that doesn't imply that it's planar. This is only necessary for it to be planar. I'm sorry to disappoint you. I mean, I'm not saying whether it is or isn't, but that's certainly necessary. What do you get for the 20-faced die?
It's also good for the formula.
So the number of vertices is how many? 20 vertices? No.
Vertices
Which one did we just do? We have how many vertices on the blue die?
20.
20, and each of degree 3, so that matches, that's okay. What about the red die? Or whatever color it is. So now I have how many vertices of degree 5?
12.
I have 12 vertices? How many vertices do I have here? How many points?
12.
Only 12? Okay, so I have 12 vertices, each of degree 5, 12 vertices of degree 5. How many edges?
30.
So that would be 12 times 5 is 60, divided by 2 is 30. So we have 12 minus 30. How many faces? 12. Sorry, 20. 12 minus 30 plus 20 is 2. Okay. So is this one? This one? Okay. So I just want to close with let's see. Let's see. So look at page 347. 347. Construct a 5 regular planar graph of order 12. 5 regular. One more time. How many vertices did you say the red die had? 12. How many edge? What's the degree at every vertex? 5. So it's 5 regular on 12 vertices. So somehow you got to show that this one is planar. Okay. Okay. So I'll let the tables take those die. You can decide who gets it. The final will be Tuesday, a week from this last Tuesday. Essentially, it will stress more about what we've done in the last 3 weeks. You know, I won't say that it's going to have 50% covered in what we did on chromatic number, the independence number versus the edge independence number versus covers. There will be some significant part about that, as well as planar graphs. Okay? And one more time, it's Tuesday at 2 o'clock. See you all Tuesday. In this room. In this room.
它这个考
Okay.
试时间好长呀。
所有考试应该都是这个时间。
它不是说要4点50吗？